Hi everyone, my name is Ahmad Alkaf and I'll be presenting about rehabilitative robotics. Stroke is typically expressed as a recovering neurological condition or a brain attack that could happen to anyone. Rehabilitative robotics is a research field which understands and enhances rehabilitation via the application of robotic devices. With rehabilitative robotics, rehabilitation can be done in a more efficient way. This project will develop a rehabilitative robotic system that will assist stroke patients with the recovery of their hand movements. The objectives of this project is developing a rehabilitative robotic system that assists stroke patients with the recovery of their hand movement, designing a 3D printed exoskeleton to be integrated with a control mechanism through a microcontroller, gathering EMG signals to understand the intent of the user, monitoring the status of the device to provide real-time feedback and assistance. Different current treatment methods can be seen which is used with the hand exoskeleton. The main design of the hand exoskeleton is to consider the purpose, the actuator type, the intention sensing method, and the power transmission. Looking at some of the existing product is the Hand of Hope. This is activated by the patient's self-initiated movements, which is recognized via SEMG, which is positioned on the forearm, and it provides visual feedback and interactive games to engage the patients while increasing the quality of rehabilitation. Another existing product is the Relap 10XO. The prototyping is done by 3D rapid printing, allowing the device to be tailored accordingly for each individual. Relap 10XO allows for grasping and lifting of daily objects as it has a maximal fingertip force of 4.5 Newton per finger. These are some examples of research paper findings. In this paper, the microcontroller controls all the linear actuators and measures the surface EMG signals. The two major muscle groups are the abductor pollicis brevis, which is the palm, and the extensor digitorum, which is the upper forearm. In this paper, the EMG signals are recorded with the Mayo armband, which is worn around the forearm and mapped to the selected gestures. The Mayo armband combines 8 EMG sensors and uses Bluetooth Low Energy for communication. In this final paper, a single motor controls 4 exoskeleton fingers. The surface EMG electrodes are placed on the forearms using a wearable acquisition system. Now the focus will be shifted towards the hand exoskeleton design. This hand exoskeleton design was inspired by Eliza Robel, a PhD fellow in the Wrocław University of Technology. The distal and middle phalange are the only parts of the fingers that can be moved. The first version of the hand exoskeleton design was 3D printed as a reference for the subsequent new hand exoskeleton designs. It was found that the hand dimensions were incorrect and certain joints were not strong enough. In the second version of the design, to fix the issue of dimension and to increase strength of the hand exoskeleton, changes were made to the joints and dimensions. Distal, middle, and proximal phalanges can now be moved. In the third and final version of the design, support for linear actuators were added. Microcontroller and motor driver were mounted in between the linear actuators. Solid core wires are used to connect between the joints to provide the user with additional room to move each finger. A close-up of the exoskeleton is shown here to understand how the mechanism works. The joint connecting the proximal phalange and the linear actuator will facilitate the movements by pulling or pushing the proximal phalange. The fulcrum joints, as seen here, will allow all the phalanges to be mobile. Now we will be looking more into the hardware components used for this project. The main hardware components used in the project is the microcontroller, which is a BLE Nano, which embeds a Bluetooth low energy transmitter receiver in the microcontroller, the linear actuator, the TFT LCD screen, and the MyoWare muscle sensor, which is used to detect EMG signals. The supporting hardware components used in this project is the motor driver, which will be used for the extension and the retraction of the linear actuator, and the potentiometer, which will be used for all the controls of the screen. Now we will be looking more into the hardware design of the project. The first hardware design which we will be looking into is the BLE Nano extension board. With this extension board, it allows for the ease of mounting, and it also increases the number of 5V and ground connections, which will then allow for more connections to be done with the BLE Nano. Now highlighted in red are the 5V connections, and the one in blue are the ground connections. Now we will be looking more into the next hardware design, which is the exoskeleton control. The exoskeleton control consists of the screen and the potentiometer. The screen is embedded together with the potentiometer and is enclosed with a 3D printed casing. With this 3D printed casing, it is easy to mount or hold the exoskeleton control. Now we will look more into the circuit connections of the project. As seen in the figure, there are 5 main components excluding the power supply. The circuit connection colors used in this figure are selected based on the actual connections of the exoskeleton. The labels seen on this figure are the connections from the BLE Nano. Now we will be looking at the hardware integration. As seen in the figure, the exoskeleton now has the BLE Nano, the motor driver, and the linear actuator mounted on top of it. There is also the exoskeleton control and the MyoWare muscle sensor, which are attached to the BLE Nano. Now we will be looking more into the embedded software implementation of this project. Upon booting up the system, the welcome message is displayed, and the instructions on how to use the exoskeleton will be displayed as well, and this display will remain for 5 seconds to allow for the user to read the instructions provided. Once the user has read the instructions, the mode configurations will be displayed. The user can select between automatic EMG or manual assistive mode. For the manual assistive mode, the user can select a range of assistance levels to be provided as seen in the figure. The 3 options for the execution states are open, close, and rest. These states apply for all modes. If the user selects the automatic EMG mode, the execution state will be displayed in cyan. Just below the execution state, the active state will be displayed in green. This active state will only be displayed whenever the user attempts a certain amount of force. A real-time graph will also be displayed in yellow, and this graph will be displayed the instant the user selects this EMG mode. Despite the execution state that the user is in, this real-time graph will always be running. If the user selects the manual assistive mode, the execution state will be displayed in green. The assistance provided will be based on the assistance level selected upon entering the mode. The linear actuator then will execute based on the assistance level selected. Each time the data is received from the MyoWare muscle sensor, the data from the BLE Nano is packaged as follows before the transmission. The format of the data packaging is as follows. This data packaging allows the data to be transmitted and received easily. The 2 types of data being sent is either of an EMG type data or from a manual assistive type of data. The embedded software overview flowchart is as follows. Upon booting up the system, the user will select between the automatic EMG mode or the manual assistive mode. The user will then select the execution state being open, close or rest. Then the linear actuator will execute according to the execution state, and the data will be sent via BLE over to the computer. Now we will be looking more into the testing of the MyoWare muscle sensor used in this project. The experimental setup is as follows. The MyoWare muscle sensor is attached on the forearm of the user as seen in the figure. The value is then read from the MyoWare muscle sensor and sent to the computer to further analyze the data. For the data collection process, 10 people has agreed to assist in this process. For each of the participants, they will have to carry out 5 different hand gestures being the resting position, the fully clenched position, the partially clenched position, the fully extended position, and the partially extended position. Now we will be looking more into the EMG data processing. After the 10 participants has successfully collected all the data, a general trend for rest state could be observed. However, for the open and closed states, the trends are very similar. Whenever the user exerts a certain amount of force, a peak is observed. This can be seen in the figure below. Based from the actual data collected from the 10 participants, we could see here that the values obtained fluctuates within a range of values. But however, the general rest state waveform trend is observed within all those 10 data collected. Based on the data collected from the 10 participants, it is seen here that the general trend for the open and closed state waveform can be observed. The peaks indicate the active states. As we see here, the amplitude of the peak increases as the force applied increases. For the data processing, maximum and minimum value across 5 data points are obtained. The formula below is applied, where the maximum values of those 5 data points are subtracted with the minimum value of those 5 data points as well. This caused the resulting data to be bounded to a more manageable range of values. This also reduces the complexity for the data processing. In the post-process waveform for the rest state, it can be seen that in the graph obtained, the data falls within the range of values and it does not exceed the rest state threshold. In the post-process waveform for open and closed state, the peak amplitudes are more visible, which simplifies the categorization process. It was observed earlier that the rest state values does not exceed 32. Hence, the categorization for the active state are done based on their post-process threshold value as seen here. The focus will now be shifted to the software implementation of the project. For the BLE communication process, the model number and characteristic UUID is used for the connection. The data is then extracted accordingly based on the BLE data packaging format seen earlier. For the automatic EMG mode, it consists of both EMG and assistive level data. For the manual assistive mode, it only consists of the assistive level data. A database is used for the data received from the exoskeleton. 2 tables are created, being the data table and the performance table. All the extracted data received will be stored in the data table. The data table can be seen here, which consists of the execution state, activation state, and the manual assistive state. After each session, processed data will be stored into performance. The data from the performance table will be used to track the performance of the user for each session. This is the main program. The graphs seen are the performance of the user for each session. On the top left corner, the status of the exoskeleton, the connect and the exit button are seen. On the top right corner, the generate report button is seen. Whenever the user presses the connect button, the program will pair up with the exoskeleton and a confirmation to run prompt will pop up. Once the user agrees to run, the data received from the exoskeleton will be stored into the database. This process will be executed for a minute, and the user will be prompted again if he would like to run. If the user decides to stop the process, the second prompt will pop up, confirming if the user wants to track his or her performance. If the user agrees to track his or her performance, a live graph of the session will be plotted. If the user presses the Generate Report button, a report will be generated as seen in the figure, which consists of the information such as sessions, attempts, EMG open and close attempts, assisted open and close attempts. Once the user has read the information, an overall session performance graph will be plotted. For both the live graph and the overall session performance graph, the graph is as follows. This is a software overview flowchart. Upon booting up the system, the welcome message is displayed, then the main program will load, and the subsequent steps for connect, generate report, and exit can be seen in the flowchart. Some of the challenges faced during the period of the project is designing the exoskeleton, limited access to the 3D printers due to technical issues, integrating the hardware components due to the absence of certain datasheets, restricted budget issues, and shipment for resources. Some of the future recommendations that could be done are as follows. Firstly, research for a more sensitive EMG sensor to enhance the performance. Then, redesign the hand exoskeleton to reduce the thickness and increase in strength. Next, assign an individual linear actuator for each finger. And lastly, integrate the exoskeleton control and the GUI with an online database. In conclusion, the presence of rehabilitative robotics has allowed the process of rehabilitation to be easier and portable. The purpose of this project is to assist stroke patients with the recovery of their hand movements. Despite this project is a prototype, it has laid out the foundations for further developments. Before I end this presentation, I would like to personally thank Mr. Ravi for being very supportive throughout the duration of this project, and I would also like to thank everyone involved directly or indirectly in the development of this project. Thank you everyone for your time.